All right, so in this part of the lecture, we are going to talk about how heat is transferred, and in particular, take a look at it in the atmosphere. But I'm going to give you several examples of it in general day-to-day living so that you can relate to it a little bit better. But a lot of what we're going to get into in future lectures and future modules will be how this is happening in the atmosphere specifically. So the three major ways in which heat is transferred is conduction, convection, and radiant energy. Conduction is actually a transfer of heat from molecule to molecule within a substance. And what's going on is you get heat applied, like this pot of boiling water here, you've got heat applied at the bottom of the pot. But you know, at least maybe with experience on cooking, if you pick up a pot of boiling water off the stove by its handle, and especially if that handle is metal, it's going to end up burning you if you wait too long. And that is due to conduction, because as the fire is hitting the bottom of the pan here and heating up the molecules within the pan, the molecules bump up against each other, and as they do so, they actually transfer the heat with that bump. And so what ends up happening is that heat ends up migrating up the pan and to the handle, where the person will eventually feel too much heat and not be able to hold that handle without protection at some point. So that's conduction. Conduction is probably the least important heat transfer in the atmosphere, at least the least effective, I should probably say instead. Mostly because in the atmosphere we're dealing with gases, and the molecules and atoms are very far apart to one another, and this is more of something that happens in solid material, and more importantly even metals. Because the atomic structure of a metal is such so that electrons are going freely from atom to atom. They're not like attached to one single atom or molecule. They can kind of just travel all over the substance, and that helps to conduct heat a bit better than maybe something like a wood countertop or plastic or something like that. So that's conduction. Conduction does play into the atmosphere a bit, and we'll talk about that later on in the course where it becomes relevant. Convection is a very important part of heat transfer in the atmosphere, and the idea of convection is that you are moving a liquid or a gas, and as the liquid or the gas is moving, it's taking heat with it. And so here you'll see that we have again that pot of water that's boiling, and you'll notice the water is physically rising up as it's heated from below. What happens is as you heat molecules and atoms up, they expand and become less dense. And so that less dense material will want to rise because it becomes more buoyant and basically lighter. So it actually will float to the surface. And that happens with liquids, but it also happens in a big way with gases in the atmosphere. A lot of what we see as far as thunderstorms are concerned have a lot to do with convection in the atmosphere and warm air rising. And obviously, if it's thunderstorms, warm, moist air rising. So that's convection. Sometimes just warm air rising, whether there's water present or not, meteorologists will call thermals. And if you're flying in an airplane and there are thermals present where warm air is readily rising, you might feel a bumpy ride in the airplane as the air pushes up on the airplane as it's traveling over. So that's something to keep in mind as far as the forcefulness of these air currents. Are not gentle. Sometimes they're actually quite dangerous for airplanes to fly over. So we'll get into convection obviously in more detail as we move forward in the course. The other way in which you get heat transferred is radiant energy. And radiant energy is something where you have basically, you'll see the picture here. Get my cursor here. You'll see that they're showing these wavy arrows moving away from the flame. And basically, it's the only way in which you can transfer heat without having a medium present. For convection, you obviously are moving fluids, whether they're gases or liquids, but you're moving substance in that respect to move the heat. For conduction, you're actually vibrating the material and having the material bounce into each other, the molecules and atoms specifically bouncing into each other to transfer the heat. So again, you need a medium to get that heat energy transferred from one place to another. Radiant energy doesn't require that. It can travel through empty space, and this is why we can get heat energy from the sun. Because the sun's energy hits the Earth's surface, to get here, it has to travel through empty space to do so. So obviously radiant energy is a extremely important part of everything we're going to talk about in relation to the atmosphere and weather, and also obviously climate as well. Let's go ahead and go to the next slide. And this is a diagram. There's a similar one in the textbook as well. But basically what it's showing you is different kinds of radiant energy. We measure radiant energy by what is called a wavelength, and there's short-wave radiation and long-wave radiation. A wavelength is simply measured from the crest of one wave. If you follow my cursor here, I'm just picking one random bump there. There's the crest of one wave, and then here's the crest of the next wave. And so the distance between one crest and another is what is termed the wavelength. And the shorter the wavelength, the stronger the radiation is actually. And you'll see we have this broken down into a short wave radiation category and a long wave radiation category. And here's the actual measurements for the wavelengths. And they can get quite large, up to 1,000 meters for the long radio wave radiant energy. Now, as far as what we're going to be dealing with in this class, we're going to be obviously looking at how the sun is delivering radiant energy. But before I talk about that, it's important to realize that any object, any substance, is releasing some measure of radiant energy. In other words, any object that you can touch, anything, let's say you're obviously sitting here watching the lecture right now, look around you and just look at all the objects around you. All of them are producing radiant energy at some level. Obviously very, very minor levels, but nonetheless everything does produce radiant energy. The hotter the body is, the shorter the wavelength is going to be. So when we're dealing with the whole Earth, we're actually dealing with the infrared part of this spectrum of radiant energy. And so for the Earth, we're sitting right in this zone here as far as wavelength is concerned. The sun delivers us infrared visible light and ultraviolet radiation primarily. And so the solar energy sits in this part of the spectrum. That's the part that's getting delivered to us. Now, for that reason, when I talk about energy coming from the sun, radiant energy coming from the sun, I actually always just refer to it as shortwave radiation. I don't really say ultraviolet or visible light. I just basically say shortwave radiation. And then if I'm talking about what the Earth is emitting as far as radiant energy is concerned, because the Earth definitely does emit radiant energy as well, it's in the long wave radiation spectrum, so I just say long wave radiation. So if I'm talking about long wave radiant energy in relation to the atmosphere, you can bet that that's actually coming from the Earth. And if I'm talking about shortwave radiant energy, I'm talking about the energy that's coming from the sun and hitting the planet. This is going to become very important when we talk about the greenhouse effect. So keep that in mind for that. Now, as far as studying for an exam and answering questions relating to an exam, I'm actually not going to test you on most of these different types of radiant energy, some in which you're probably familiar with, like X-rays, microwaves, television film, television and FM radio, excuse me, shortwave radio, all those kind of things you've heard of before. I'm not going to test you on those. In fact, I'm not even going to test you on the wavelength size of this radiant energy because I'm not really concerned that you know that going forward in your life. But I do want you to be aware of shortwave radiation and longwave radiation and what the sun is emitting versus what the earth is emitting, because that does become a big deal when we talk about the greenhouse effect and what that means. All right, so let's go ahead and talk about how radiant energy is handled in the atmosphere. Let's go to the next slide. So radiant energy can reflect and scatter. And I want to talk about what those terms mean specifically. Reflection in science, whatever you're talking about as regards to waves, basically. Waves can come in and reflect, and what that simply means is they come in at an angle and then they hit an object like maybe a water droplet in the atmosphere or something on the Earth's surface. That radiant energy would come in, hit it, and then go out at the same angle and the same intensity. That's what reflection represents. So if you imagine this being a solar energy coming in, shortwave radiation coming in, hits this water droplet in the atmosphere and then goes right back out again at the same intensity, what you're saying is none of that energy reached the Earth's surface at all. Something in the atmosphere effectively allowed it to hit it and then make it go right back out without coming anywhere near us, for example. So that could happen in the atmosphere. The other thing that can happen in the atmosphere is scattering, where a radiant energy will come in, like a sun ray will come in, hit something in the atmosphere, maybe some particulate matter, maybe that has an uneven surface or whatnot, and then the energy will scatter in all directions, where some of it will hit the Earth's surface and some of it will go back out into space. And it's important to realize with scattering that the same energy that's coming in, when it scatters, if you added up all the scattered rays, it does equal the intensity of the ray coming in. So you're not losing energy or gaining anything from the scattering process. And in fact, that's the same with reflection as well. You're not gaining or losing energy. The same energy coming in as going out for reflection, and for scattering, it's the same energy coming in, and then you add all the rays that scattered, and it equals that incoming ray, that incoming original ray. All right, let's go ahead and go to the next slide now. I want to talk about some other concepts in relation to reflection and scattering. So there's a term we use in meteorology and climate called albedo, and if you've done any kind of just casual reading with climate and climate change type of texts or novels or books or whatever, albedo is going to be a very common word you'll hear. Albedo refers to the reflectivity of a surface. So if you have a surface that really is very reflective, it also means it has a high albedo. And the rule of thumb mostly is the lighter the color of the surface, the more reflective it is, and also means the higher albedo it has. So fresh snow reflecting, it's very light color. Fresh snow is very white. It's obviously going to be very, very reflective, and in fact it typically reflects 80 to 90% of the energy coming in. So we'd say that fresh snow has a high albedo. And in fact, if you go skiing, normally you're bundled up anyway because it's cold when you're, playing around in the snow. But it's also very important to make sure you're covered up as far as sunblock is concerned, any exposed skin, because that same energy that's coming in and hitting you from the sun is also reflecting off the snow around you and coming right back up at you again. So you're actually getting a double whammy of solar energy when you are dealing with albedo and high albedo of the snow. So that's something to keep in mind. You'll see other things on the list like old snow has a lower reflectivity because it's dirty, so it doesn't have as much reflectivity. And then you can see other things on the list as well. Something I wanted to bring to your attention that typically, if I don't bring it up, gives a student's question is thick clouds. You'll notice thick clouds have a albedo that's very high. But if you look up at the sky and you got a thick cloudy day out, that usually means that the clouds are dark when you look up at them. That doesn't seem to equal a high albedo, but they're actually, the very thick clouds are actually that. They have that's not a typo. Thick clouds can have a very high albedo. So my question to you is, how can that be? How do thick clouds have a high albedo? So I'm going to give you a moment to think about it. So give yourself a second to just pause and reflect. No pun intended there. On why thick clouds would have a high albedo. Okay, if you're still thinking about it, go ahead and hit pause. That's the beauty of listening to this as a recording. You can pause me and think about it some more. Otherwise, realize the vantage point in which you are looking at the clouds. You're looking at the clouds from the bottom up. But where is the sun in relation to those clouds? Well, obviously the sun's out in space. And if any of you have taken an airplane trip from an airline, so take a big jet plane and you go basically thousands of feet up above these clouds, these very thick clouds, you'll notice that they're very white on the top. And so the sun energy is coming from that direction, that vantage point. So in that side of the clouds, it's very reflective. From underneath, because you're on the opposite side that the sun is on, the clouds appear dark to you, because the sunlight's being blocked because you're on the other side of the clouds from the sun. So you're not going to deal with the albedo in relation to sunlight from down there because the sun's on the other side, and on that other side those clouds are puffy and white and therefore will have a high albedo. So thick clouds can be very effective at reflecting radiant energy. Thin clouds, on the other hand, you'll notice the percent reflective is much lower albedo, and that's because if you look at it from our vantage point, they actually appear very white in color. If you look at any high clouds, they're usually thin and wispy, but they're always pretty white. But if you look at it from the vantage point that the sun is, they actually appear dark. So then therefore have a lower albedo as a result. When you total the entire Earth and atmosphere overall from poles to the equator, the albedo averages about 30%. But realize that the poles are going to have higher albedos because of the glaciers that are present there. And then the albedo will lower significantly as you go toward the equator, where you lose the snow and you have more darker colored materials on the surface. Okay, let's go ahead now and go to the next slide. So scattering is actually interesting in and of itself, because what that produces is the blue sky that we see during the day when there's no real clouds out or very few clouds out. Basically, we get blue sky from scattering because the molecules in the atmosphere are actually more effective at scattering short wavelengths. And if you look back at the spectrum that I showed you earlier, if you follow my cursor, there is the visible light spectrum, and notice that blue is on the short wavelength part of the visible light spectrum, where the reds and oranges are more on the longer wavelength part of the spectrum. So we basically see blue sky straight above us, because if you look straight up above you in the sky, what you actually are seeing is the atmosphere that's closest to you. If you look far out in the horizon, in the distance, that atmosphere is much further away from you than you looking straight up above you, because that atmosphere is right there above you. And so you're going to see blue, real deep blue skies straight above you in that closer atmosphere, because the atmosphere is scattering effectively the blue part of the spectrum so your eyes can see that better. Notice in this picture, if you look out in the distance, notice how it gets washed out and mostly like a light blue to maybe even white in color. That's because the distant sky is so far away from your eyes that the blue light scatters away before it reaches your eyes when you're looking at that distance. But notice as you look up in the pictures, you get closer to where that person's taking the picture, the sky starts to turn a deeper blue. So that's why. Let's go to the next slide. So a lot of you have seen beautiful orange and red sunsets, and this is because of the position of the sun in the distant horizon. So in the distant horizon, while the sun is setting, normally when the sun is up high and not in that position, the sky over there would look washed out, a whitish color there. But now that the sun's positioned there, you start to see the longer wavelength spectrum of color from the visible light spectrum of the sun reaching your eyes. And the blue would not still appear there because the blue is short, and it's shorter, and it scatters away before your eyes can see it. But the longer wavelengths with the sun position right there will reach your eyes effectively. And so that's what actually gives you the nice brilliant colors of the orange and red, and sometimes looks even pinkish sunsets. Let's go ahead and go to the next slide now. And why are clouds white then? Well, we've talked about clouds being dark and already, with being where you're at in vantage point to where the sun is at on the opposite side of the clouds. That kind of blocks out the light and makes them look dark. But when you have high clouds like this, the water droplets are actually much bigger than molecules. So when we're talking about scattering of atmospheric molecules and light, it's a much different thing than talking about water droplets, because those are actually much bigger. Your eyes can see that actually. But what that does also is scatter the visible light equally in all directions, so that it makes your eyes just see white instead of any kind of particular color. So that's why they're white. All right, so this is the end of this part of the lecture segment. I will see you in the next one. Thank you very much.